Hello everyone. Today I'd like to introduce the first chapter of the book, named Review of Monolithic Microwave Integrated Circuit Technology. And I'd like to introduce from these four parts. First one is Introduction to Integrated Circuit Technology. And the first is definition of integrated circuit. Radio frequency refers to a series of frequencies in the electromagnetic spectrum that are higher than the audio range, but lower than infrared light. All wireless transmissions use radio frequency, including AM and FM, broadcasting, television, mobile phones, and wireless networks, and so on. Radio frequency signals can be focused in one direction or transmitted in all directions. Microwave refers to radio signals with a frequency range greater than or equal to 1 GHz. Many transmission systems use microwaves, including line-of-sight communication between buildings and long-distance communication, satellites, personal communication system, and wireless local area networks. Therefore, integrated circuit is an integrated circuit used for high-frequency applications such as mobile phones. MMIC combines transistors and passive components on the same chip, and is widely used in telecommunications as amplifiers and filters. It can be in analog only or a mixed mode of analog and digital. Its operating frequency range ranges from 1 GHz to over 100 GHz. Therefore, in MMIC, making this technology applicable to all types of wireless communication systems. Frequency is defined as the number of vibrations per second, measured in hertz, equivalent to oscillations per second, or cycles per second. For example, the frequency assigned to a radio station is defined by the International Telecommunication Union radio regulations as the frequency band center assigned to a station. In fact, the frequency assignment is the actual radio frequency of the signal being transmitted and received. This is the most commonly used frequency designation. The assigned frequencies for different purposes are shown below in Table 1.1 and Table 1.2. And milestones include the silicon integrated circuit technology launched in 1964, which aims to build transmission and reception modules for phase array radar antennas. However, due to the poor semi-insulting properties of silicon, the results were disappointing. Therefore, in 1968, someone used semi-insulting gallium arsenide substrates, and another two people deduced as active devices to manufacture a 94 GHz front-end receiver. Subsequently, someone used MOSFET device on gallium S and manufactured an expand amplifier in 1976, which sparked intense activity in gallium S MMICs. Around 1988, DARPA launched a large-scale research and development project called the MMIC program. The results of this work have led to the emergence of commercial applications such as DBS TV receivers, automotive collision avoidance radar, wireless local office computer networks, and personal and cellular communication. And next one, in table 1.3, it's shown a comparison between MMIC and hybrid MICs. In table 1.4, it's shown the advantages and disadvantages of the MMIC. And there are many fields of application for MMICs. Table 1.5 presents the development of MMIC technology makes convenience in widely applied fields like military, space, and civil. And the second one is some substrate materials of MMIC. In this second section, I will introduce various substrate materials used in MMIC technology, such as silicon, gallium arsenide, silicon germanium or silicon carbide, and gallium nitride. The first one is gallium nitride, gallium arsenide. It is an alloy used as a substrate material for manufacturing semiconductor chips. It has many advantages, such as gallium arsenide having a higher saturation electron drift rate and lower field mobility than silicon, and running at a faster speed. At the same time, it has high resistance, and gallium arsenide devices uh, generate less noise than silicon devices. In addition, it has lower power consumption performance. Finally, due to the direct bandgap property of gallium arsenide, it can be used for optical transmission in optical devices. And the second one is silicon. Silicon is more widely used in semiconductor manufacturing because the reverse leakage current of germanium is 6 orders of magnitude higher than that of silicon at 25 temperature. Compare, Compared with gallium arsenide, silicon has high strength, is easy to process, and has an excellent passivation layer suitable for planar integrated circuits. Therefore, due to the high output during the manufacturing process, low-cost silicon devices can be obtained. However, the production of gallium arsenide is low, and the devices manufactured are more expensive than silicon devices. And the third one is silicon germanium. The migration rate of silicon germanium is better than that of silicon, and its thermal conductivity is also better than that of gallium arsenide. Meanwhile, the cost of silicon germanium devices is lower than that of gallium arsenide devices. Silicon germanium device manufacturing is compatible with the standard silicon manufacturing process used for producing higher frequency circuits. Only a small number of silicon germanium transistors are used in mobile phones, while thousands of silicon germanium transistors are used in fields such as optical switches, DACs, and ADC. And the fourth one is silicon carbide. Silicon carbide is an alloy of silicon and carbon with a wide band gap. Its electron saturation rate is higher than that of silicon and gallium arsenide, but the difficulty and cost of manufacturing single crystal silicon carbide chips are high. The wide bandgap energy, high thermal conductivity, high saturation, electron drift velocity, and high breakdown electric field characteristics of silicon carbide. Silicon carbide can appear in many different crystal forms, with high hardness, strong chemical stability, and resistance to radiation damage, making it suitable for high radiation environments. It is available in both conductive and semi-insulting substrate forms. And the fifth is gallium nitride. This compound is a very hard material with a voltage crystal structure. It has a broad band gap and is less sensitive to ionizing radiation, making it suitable for use in cities. These devices exhibit stability in radiation environment. It can operate at significantly higher temperatures and voltages. Gallium nitride is a very hard, magnetically stable, and wide bandgap semiconductor materials with high thermal capacity and thermal conductivity. In its pure form, gallium nitride has the characteristic of resisting cracking. Meanwhile, gallium nitride compounds also tend to have high spatial defect frequencies. And this text mainly introduces several technologies and main active devices used in microwave integrated circuit, including gallium arsenide MOSFET, gallium arsenide HEMT, and so on. And the selection of these devices depends on factors such as electron drift, saturation speed, mobility, and resistivity. And the first one, gallium arsenide MOSFET, is the earliest microwave transistor that can be easily mass-produced through ion implantations, with advantages such as high saturated electron drift speed, low field efficiency, and high resistivity. The structure and equivalent circuit of gallium arsenide MOSFET are shown in figure. The image shows the basic structure of p-HEMT, which is a two-dimensional electron gas structure. The active layer is provided as an epitaxial wafer. They contain single and double heterojunction transitions, which provide high electron mobility in two-dimensional electron gas. The epitaxial layer is mainly grown by molecular beam epitaxy, which increases the cost. But metal, organic, chemical, vapor deposition is also used in same manufacture process. It exhibits the lowest noise figure and high gain, but due to its strong oscillation, it may not be a good choice in low-frequency applications. And this shows a cross-sectional schematic diagram of an MHAT device. It is the most mature gallium arsenide device structure. These structures contain a component gradient buffer layer to extend the lattice constant. The key issue in the operation of EMT lies in the heterojunction interface between two semiconductor materials with different band gaps. The energy gap of aluminum gallium nitride is higher than that of gallium nitride. Silicon impurities donate electrons to crystals. The electrons have a tendency to accumulate in the lowest potential region, known as quantum wells, located directly below the aluminum gallium nitride interface. This forms a layer of electrons forming two-dimensional electron gas. And 35 compound HBT is a modified BJT, which is implanted through wide bandgap emitter region and narrow bandgap base region, and can operate with a single power supply with characteristics such as high power density and output independence. Figure A provides a schematic cross-sectional view. The equivalent circuit of 35 compound HBT is shown in the figure B. Silicon germanium HBT can achieve higher electron mobility and lower noise due to the difference in lattice consistence between silicon and germanium, which enhances its competitiveness with gallium arsenide circuit in some applications. The main structures and their bandgap diagrams are shown in these figures. And the typical features of silicon BJT devices include an emitter width of 0.4 micrometers, dual self element technology, sidewall spacing technology, buried layer, and selective implantation of collector electrodes. There is great potential in manufacturing highly integrated circuits. The schematic diagram of high-performance silicon BJT is shown in the figure. In silicon CMOS achieves high mobility of electrons and hole through strain silicon technology, thereby improving the drive current of CMOS transistors and achieving faster and more stable processing. And this section introduces the description of passive components used in MMIC design. MMIC inductors can be achieved through narrow track, single coil inductors or multi-coil spiral inductors. The choice of inductor depends on the required inductance of the circuit and its implementation in the circuit. MIN capacitors has high electrical capacity per unit area and can be used for MMICs. This type of capacitor consists of two metal plates separated by dielectric materials. The dielectric materials between two metal plates usually overlaps on the first layer of metal, and the area of the upper layer of metal is smaller than that of the lower layer, which helps to reduce the edge effect of the field on the ground. Resistors are used for feedback circuits, setting bias points for active devices, isolating and terminating in power combiners and couplers. In MMIC manufacturing, two types of resistors are used, including lost metal thin films and lightly doped gallium arsenide active layers. Transmission lines are used to guide energy from one point to another. For MMIC purpose, microstrip lines are usually used, although coplanar waveguide transmission lines can also be used. The combiner is used to merge two or more transmission lines into one transmission line, and can also be used to divide the microwave signal of a transmission line into two or more transmission lines. The isolator allows microwave signals to pass in one direction but not in another, which can be achieved by using ferrite. The circulator routes microwave signals from one port of the device to another. And through holes are used to connect different metal layers in integrated circuits, and can also be used to electrically connect the two sides of the silicon chip. It can be applied to 3D packaging, microelectromechanical system, or multi-chip stacking. Both microstrip line and backgrounded coplanar waveguide technologies required through-hole to provide microstrip short circuit or connect to the upper and lower ground planes of the coplanar waveguide. Through holes are usually formed by attaching the back of the gallium arsenide substrate to reduce the top component area. Air bridge or cross bridge are necessary for most integrated circuit layouts. It is a simple metal bridge that allows two transmission lines to cross each other without forming a short circuit. By connecting cables and winding paths, DC bills can be provided and the signal can be output. And the use of interconnections in integrated circuits is to accurately model and avoid unnecessary resonance. And this is my presentation. Thank you for your listening.